Okay, so welcome back to another video. So in today's video we have a little proof that we want to show. So we have the inequality 1 over b is less than ln of b minus ln of a divided by b minus a is less than 1 over a, such that 0 is less than a is less than b. So this inequality actually has a name to it. This is known as Napier's inequality, named after the mathematician John Napier, who motivated this whole idea about the natural logs and logarithms himself. So the whole idea of this inequality is you'll see that if I plug some following Cartesian coordinates, so if I plug a and using the function, the natural log function, so if we were to plug a, our output would be ln of a, and if I plug b, we get our output that is ln of b. So you'll notice that the slope at the point a is the slope is actually bigger than the slope when the point is at b. And you'll see that the reason we have this natural log minus b, natural log b minus natural log a divided by b minus a, that's the slope. So if we were to consider those 2 points and connect them together to form some secant line, you'll see that the slope of that secant line lies between these two inequalities of the slope itself, those slopes, I mean. So that's why we have this inequality, and in today's video we're just going to prove the following inequality. So with that, let's just jump right in. To do this, I want to prove two of the following cases. I want to prove that x is less than 1 and x is greater than 1. So how about we start off with the first case, that x is greater than 1. So notice for x is greater than 1, okay, then we know that the natural log of x is actually equal to the integral from 1 to x of 1 divided by t dt. And we know that t is in the element, the open interval from 1 to x. I don't know why I wrote 0. The open interval from 1 to x, and then with the condition that x is greater than 1. Okay, cool. So from there, we actually note that using these two conditions, we can see that 1 over t is strictly less than 1. Okay, now using this condition, we write the same thing as before. So the natural log is equal to 1x 1 over t dt. And then I'll use the inequality from here, but I would have to take the definite integral of 1 from our bounds from 1 to x. So 1 to x dx, and you'll see that if I calculate this definite integral, we get that this is x minus 1. Using the condition that 0 is less than a is less than b, then you'll start to see that b minus a is greater than 1. So now let's substitute x equals b divided by a. So from here, so the natural log of b divided by a, you'll see that's from the extreme left hand side, that's less than from the extreme right hand side, so this will be less than b divided by a minus 1. Now if I simplify this out a little bit, using the rules of natural logs, I can write this as a difference of natural logs, so it's the ln of b minus ln of a, which is strictly less than, so get a common denominator, so this is b minus a divided by a. And then I'll just divide b minus a to both sides, so we get that the natural log of b minus the natural log of a divided by b minus a is strictly less than 1 over a. All right, so that's one side proven. So I'll just mark this black box just to show that we proved one side of on one side is complete. So with that, now let's actually prove the other case. For x is strictly less than 1. Okay, so notice for x is strictly less than 1. So we know that the natural log of x is equal to the negative integral from our bounds this time is going to be from x to 1 of 1 over t dt, with the fact that t is in the open interval from x to positive 1. And now using the condition that we have that x is strictly less than 1, and then with t is in the interval from x to 1, you'll start to notice that negative 1 divided by t is strictly less than negative 1. Okay, So using this condition, we'll see that the natural log of x used from the extreme left-hand side, this is equal to x, the integral from x to 1, the negative of, so it's positive 1 divided by t dt, and then use our strict inequality, and then take the definite integral of -1. So the negative definite integral from x to 1 of dx, 1 dx, and you'll see that that's actually just equal to x minus 1. You'll start to observe that for, again, back to the same condition, 0 is less than a, which is less than b, then you'll start to see that a divided by b is actually less than 1. So now let's substitute x equals a divided by b. So plug this back in. Ln of a divided by b is strictly less than over here, so a divided by b minus 1. Simplify this out even further, use our rules of natural logs. This is the natural log of a minus the natural log of b, which is less than a minus b divided by b. Okay, and now I'll just divide everything by both sides. So let's see, that will be the natural log of a minus the natural log of b divided by a minus b. But be careful now. So because we had that a is less than b, so a minus b means that we're going to get a negative number. So this means when we're dividing a negative number, we had to actually switch our inequality sign. So therefore, we end up with greater ln of a minus ln of b divided by a minus b is strictly greater than 1 divided by b. Okay? And with that, we have proved both sides. And now we've just combined some things together. I want you to note that the following are two inequalities. So note that the natural log of b minus the natural log of a divided by b minus a is exactly the same thing as the natural log of a minus the natural log of b divided by a minus b. And it's kind of self-explanatory. You can actually just rearrange some terms around and it's still commutative under addition. It still works the same, so it's actually not that difficult to see from here that why the equality is true. And we're actually pretty much done here. So we just combine our inequalities together to get a little compound inequality. So we have that 1 over, that's supposed to be b. So we have that 1 over b is less than ln of b minus ln of a divided by b minus a, and I set that because we set the equality. So this comes from ln of a minus ln of b divided by a minus b. We set that that's equal to this, which is what we're trying to show, which is coming from here, and then we set the strict inequality that is less than 1 over a, and therefore we have proven our inequality, like so. There we have it in this black box. All right, that's pretty cool if you ask me.